Hello and welcome. This is an example of relative growth rate using L'Hopital's rule from Calculus 2. This is going to be similar but not exactly the same as one of my discussion boards in my Calculus 2 course called relative growth rate. So the problem is written here. I don't know if you can see it. I can make it a little bit bigger. So what it says is determine if the following functions grow faster, slower, or at the same rate as the function e to the 2x as x goes to infinity. Alright, and what we're going to be doing here is the details of this are written out on your discussion board problem, but I'm still going to be going through all the steps here. So the basic idea is you write this as a fraction, and then you turn it into an infinite limit. And if the numerator is growing faster than the denominator, the value of the limit will be infinity. Whereas if it's growing at the same rate, it will be a constant other than 0. And then if it's growing slower, it'll be 0. Okay? So let's go ahead and start with part A. Okay, so for part A, we want to determine if x minus 5 is growing faster, slower, or at the same rate as e to the 2x. So what we're going to want to do here is, just like on the discussion board problem, you want to rewrite it as an infinite limit. So here you can see limit as x approaches infinity of, we're going to have e to the 2x on the top, and then on the bottom we're going to have x minus 5. Okay. So infinite limit as x goes to positive infinity. Well, our numerator is going to be e to the 2x. That's this right here. That's our numerator. And then our denominator, well, for part A, our denominator is going to be x minus 5. Okay, so I circled that in blue. Alright, so that's how you set up the problem. You take your original function, you put it in the numerator, and then you take the function that you're comparing it to and you put it in the denominator. And then based on what you get for this limit, that's going to determine whether either 2x is growing faster, slower, or at the same rate. Okay? Now the thing is, if we just go ahead and do this limit the way it's written, in the numerator we're going to get e to the infinity, I'll put quotes around that, and in the denominator we're going to get infinity minus 5. Again, I'll put quotes around it because that's not exactly, 100% real math to write e to the infinity. You can't exactly just plug it in, but you think about it, e is a positive number, so if you raise it to the infinity power, it's still going to be infinity. So basically what we have here is, in the numerator we have infinity, and in the denominator, infinity plus or minus any number is still infinity. So in the denominator we also have infinity. So we have infinity over infinity if we just plug in infinity here. Well, that's no good. That's called an indeterminate form. Okay, so this thing right here is indeterminate. And indeterminate is not an answer, okay? If you ever get indeterminate, that means you have not determined the answer. Okay, it's indeterminate, which means you aren't done yet. Okay, so since it's indeterminate, what we have to do is we're going to have to use L'Hopital's rule, and then we're going to have to try to find the limit again. So remember, for indeterminate, usually it's 0 over 0, but in this case it's infinity over infinity. And you might be thinking, well, isn't infinity over infinity just 1? And the answer is no. It's actually indeterminate because they're different sizes of infinity, so you can't think of infinity as just a single number. It's something that goes on forever. So infinity over infinity is not a real number. It's indeterminate. And it's not 1. Even though it looks like it might be 1, you can't cross out the infinities. Okay, so what do? You apply L'Hopital's. Okay, so apply L'Hopital's. And hopefully you've already done my homework or watched my other video on L'Hopital's. Because to do L'Hopital's, all you have to do is take the derivative of the numerator and the denominator. Okay, so when we do that here, we're going to get the limit as x goes to infinity. Well, the derivative of e to the 2x is going to be e to the 2x times 2. Okay, so in our numerator, we're going to have e to the 2x times 2, because that's the derivative of the outer function, and the derivative of e to the u is just e to the u, times the derivative of the inner function. Well, the derivative of 2x is 2. Okay, so that's our numerator, and then our denominator is going to be the derivative of x minus 5. Well, the derivative of x is 1, and the derivative of negative 5 is 0, because negative 5 is a constant. Okay, so in our denominator, we're actually just going to have 1 now. Okay, so what we've got here is e to the 2x times 2 all over 1. Now, if we want to, plug in infinity again, we're going to get 2 times e to the 2 times infinity all over 1. Well, any number over 1 is just a number. Well, what is that going to end up being? Well, if this is infinity, 2 times infinity is still infinity, and e to the infinity is still infinity, and 2 times infinity is still infinity. So this whole thing right here is basically just infinity. All right, so what does this mean? This is no longer indeterminate. So we don't have infinity over infinity. We actually just have infinity over 1, which is infinity. So what does that mean? Well, this was actually one of the cases that I talked about in the discussion board in your written instructions. So if you end up with the value of the limit is infinity, that means the numerator is growing faster than the denominator. Because this is really, if you think about it, it's infinity over 1. So that's showing that the numerator is growing infinitely faster than the denominator, so to speak, because we're plugging in infinity here. But all it really means is that the numerator is growing faster than the denominator. Okay? So that's what this means. Infinity over 1 is the same as infinity, and that just means numerator is growing faster than the denominator. Numerator is growing faster than the denominator. Okay, and that's actually the first case. Okay? All right, so I wanted to get through the rest of these, so I'm going to go pick up the pace a little bit. So this means that e to the 2x is growing faster than x minus 5. So that's actually going to be our answer. Okay, so e to the 2x is growing faster than x minus 5. Okay, but that's not actually what they asked. They asked to determine whether each of the functions grow faster, slower, or at the same rate as the function e to the 2x. So in the order that they wrote it, since e to the 2x is growing faster than x minus 5, that's the same as saying x minus 5 is growing slower than e to the 2x. Right, because that was the order that they wrote it in. They wanted the x minus 5 to be first and the e to the 2x to be second. Okay, so I talked about that one in a lot of detail, but for the other ones, I'm going to go through them a little bit more quickly because I think we get the idea now. Okay, so that was part A. Part B, we want to compare e to the 2x to 2x squared plus sine squared of x. Okay, so part B, we're comparing e to the 2x to 2x squared plus sine squared of x. Okay, and once again, the way we determine that is we put e to the 2x in the numerator, and we put our other function in the denominator, and then we take the limit as x goes to infinity. Okay? Now, once again, if I just plug in infinity, I'm going to get infinity over infinity, which is indeterminate. Okay, so what do I have to do? I have to do L'Hopital's, just like the last one. So I take the derivative of both the numerator and the denominator. So that in the numerator, we're going to get 2e to the 2x. And then in the denominator, we're going to get the derivative of 2x squared using the power rule is going to be 2 times 2 is 4x. And then the derivative of sine squared of x is actually going to be 2 times sine of x times cosine of x. Now how did I get that? Well, sine squared of x is the same as sine of x to the second power. Okay, and that's a composite function. So using the chain rule, I go ahead and I bring the 2 out front. So I'm using the power rule for the outer function. So that gave me 2 times sine of x. And then I multiply that times the derivative of the inner function. And the derivative of sine of x is cosine of x. So you get 2 sine of x cosine of x. Now the thing is, once again, if I plug in infinity in this problem, I'm still going to get infinity on the top and infinity on the bottom. So I'm going to get infinity in the numerator and infinity in the denominator. So this one is also indeterminate. So what does that mean? That means we have to apply L'Hopital's one more time. Okay, so if we do L'Hopital's again, in the numerator, we're going to get 4e to the 2x. And then in the denominator, we're going to have 4 plus the derivative of 2 sine of x cosine of x. Now, I don't know if you remember this from pre-calculus, but 2 times sine of x cosine of x is the same as sine of 2x. And that's actually in our formula sheet. If we go to our formula sheet in Canvas, let me bring that up real quick here. Depending on which course you're in, it's usually in the week 2 or week 3 module. Formulas from Calculus 1 and Calculus 2. It's a PDF. You open it up, and on the second page of this PDF, we have some things from trigonometry. We've got the unit circle here, and then we also have some identities. So the identity I wanted to show you was sine of 2 theta equals 2 times sine of theta cosine of theta. So here, instead of writing 2 times sine of x cosine of x, we're going to write sine of 2x, because that's easier to take the derivative of. Okay, so this 2 sine of x cosine of x, I can replace this with sine of 2x, just because that's easier to take the derivative of. Okay, so then when I take the derivative of sine of 2x, I take the derivative of the outside function, which is sine. So that's going to become cosine of 2x, and then I multiply that times the derivative of the inside function. So the derivative of 2x is 2. So that's going to be cosine of x times 2. Now this time, if we plug in infinity, what happens in the numerator is once again we get infinity in the numerator, because e to the infinity is infinity. Okay? But in the denominator, what do we get here? Well, we get 4, right? So we have 4 plus, what does this 2 cosine of 2x do? Well, remember that cosine just goes up and down, it oscillates. So this right here, the cosine of 2x times 2, just oscillates. But it does not go to infinity, is the important thing. So it's just going up and down from 2 to negative 2 over and over again. But what that means is that this is actually just going to be 4 plus an oscillating function. And you don't really care about the oscillating thing when you're talking about an infinite limit, because with the oscillating function, it's not going to infinity. So you can really just think of it as like infinity over 4, which is infinity. Okay? Because infinity over any positive number is just going to be infinity. And you know, it'll go up to 6 it'll go up to 6 in the denominator, and then it'll go down to 2 in the denominator. But you know, that's not going to make that big of a difference. So it's still going to be infinity. Okay? And infinity is not indeterminate. Infinity is actually the value of the limit. So just like with the last problem, if you get infinity, that means your numerator is growing faster than your denominator. Okay, so here, that means that 2x squared plus sine squared of x is growing slower than e to the 2x. Okay. So numerator is growing faster than the denominator. And the reason it's called relative growth is, relatively speaking, the numerator is growing faster than the denominator. And the reason we got infinity is because we plugged in infinity. Okay? So that means the denominator is growing slower than the numerator. Okay? So that means 2x squared plus sine squared of x is growing slower than e to the 2x. So 2x squared plus sine squared of x, that was our denominator, is grows slower than the numerator, which was e to the 2x. Okay, so that one's actually probably the hardest one. So now let's look at the other ones. So that's probably the most challenging one, just because you have to take the derivative multiple times. So for the next one, for part C, we're going to compare e to the 2x to the square root of x. So once again, we're going to write it as a fraction. And we're going to do an infinite limit. So the limit as x goes to infinity of e to the 2x over square root of x. So what we can do here is, if we plug in infinity, we're going to get infinity on the top and infinity on the bottom. So we get infinity over infinity, which is indeterminate, which means we need to go ahead and use L'Hopital's. So when we do that, in the numerator, taking the derivative, we're going to get 2e to the 2x. And then in the denominator, the derivative of square root of x, we've done it many times, is 1/2 over, so it's going to be 1 over 2 square root of x. We've done it so many times, I don't want to do it again. So it's just going to be 1 over 2 square root of x. Okay. So what happens now if I go ahead and plug in infinity again? Well, in the numerator, I'm going to get infinity. And in the denominator, I'm going to get 1 over infinity. Because plugging in infinity into 2 square root of x is still going to be infinity. So we have infinity over 1 over infinity. So what does 1 over infinity go to? That's an interesting question. Well, I don't know if you remember this from Calculus 1, but 1 over infinity is actually 0. Okay? So this is actually 0. Okay, so what we really have here is infinity over 0. So that might be another thing that you don't remember from Calculus 1. What is infinity over 0? Well, it's definitely infinity, because infinity is already infinitely large, and if the denominator is 0, I would say that's infinity. However, if you wanted to, you could keep going and you could take the derivative again. But this is definitely going to be infinity. Okay, so if it's infinity, once again, that means that the denominator is growing slower than the numerator. Okay, so that means our square root of x grows slower than e to the 2x. Okay, so the reason infinity over 0 is infinity is infinity is infinitely larger than anything, especially 0. Okay, so we're just gonna say that that's infinity. And another way you could think of it, if you don't like the infinity over 0 business, is here when you're doing 1 over infinity, you can flip that over and move it to the numerator. So if you wanted to, you could think of it as, well, you got the infinity over 1 over infinity, but that's going to be the same as infinity times infinity. So if infinity over 0 makes you uncomfortable, you can think of it as just taking the reciprocal of 1 over infinity, because dividing by a fraction is the same as multiplying by the reciprocal. So that just becomes infinity times infinity, which is infinity. Okay? All right, so for the first 3 examples, we've gotten infinity for all of them. So for all of those, each denominator grows slower than the numerator. So let's take a look at part D. So for part D, we actually have 5 to the 2x. So we want to compare 5 to the 2x to e to the 2x. Okay, so for part D, we're going to be doing the limit as x goes to infinity of e to the 2x over 5 to the 2x. Now this one's pretty interesting. So if you just plug in infinity right at the beginning, you're going to get infinity over infinity, which is indeterminate. So right off the bat, you want to do L'Hopital's rule. Okay, so if we do L'Hopital's rule, in the numerator, we're going to get 2e to the 2x, taking the derivative. And then in the denominator, well, what is the derivative of 5 to the 2x? Well, the derivative of 5 to the u is going to be ln of 5 times 5 to the u. So it's going to be ln of 5 times 5 to the 2x. And then that's going to be multiplied by the derivative of 2x, which is actually going to be 2. Okay, and then the 2's are going to cancel out. Okay, so we're actually just going to have e to the 2x over ln of 5 times 5 to the 2x. Okay, so e to the 2x over ln of 5 times 5 to the 2x. Now the problem here with this limit is if we plug in infinity again, we're still going to get infinity in the numerator and infinity in the denominator. So what we're going to have to do with this limit is we're going to have to be a little bit more creative. Okay, so how can we be more creative here? There's a lot of different approaches you can take, but the one that they use on my math lab I actually like really well. So what is the trick here? So as you can see here, if we do this limit again, we just get infinity over infinity, and you could just keep doing L'Hopital's over and over again, but you're still going to get infinity over infinity, which is indeterminate. So L'Hopital's is not going to work here. I mean, it works, but it doesn't help, because we keep getting indeterminate over and over and over again. So what's the trick? Well, actually, if we go back to the original problem, limit as x goes to infinity of e to the 2x over 5 to the 2x, we can actually rewrite this as e over 5 raised to the 2x power. Okay? So here's the trick. The trick is we write as limit as x goes to infinity. So we're writing the original limit limit as x goes to infinity of, well, we're basically just going to take this exponent, which is 2x, and we factor it out of the entire fraction. So we're going to get e over 5 quantity to the 2x. Okay, so we're going to have e over 5 quantity to the 2x. And then what about e over 5? I mean, what kind of number is that? What is e over 5 even? What is that? So if you plug it into your calculator, that's probably the easiest way to work with it. So if we do e divided by 5, that gives us 0.543 or 0.544. So this is approximately the limit as x goes to infinity of 0.544 to the 2x. So now what happens when you raise a decimal between 0 and 1 to infinity? What does that become? Well, what it actually becomes is that actually goes to 0. Now, how do we know that it goes to 0? Well, one thing you could do is you could just plug in increasingly large values for x, because as x is going to infinity, you're going to see that the limit's going to get smaller and smaller and smaller. So if I plug in x equals 1, the limit is going to be, we're going to have 0.544 squared. Okay, so we're going to get 0.544 squared, which is 0.29. We'll just say it's 0.3. But if I plug in a larger number like x equals 1,000, I'm going to get 0.544 to the 2,000, which is actually going to be a really small number. The calculator might not even do that. So if I do 0.544 to the 2,000, I'm going to get a very small number that's very close to 0. Okay, so this is approximately 0. It's going to be 0.00000, and it's going to go on for like 529 digits. But as we can see, as we plug in larger and larger numbers, this limit is going to just, for example, if I plug in x equals 1,000,000, I'm going to also get 0. Okay, So as we can see here, just by plugging into our calculator, we can figure out that this limit as x goes to infinity of this is actually just going to be 0. And that's called finding a limit numerically, which is a nice thing to fall back on if nothing else works. Okay, so if the limit is 0, if we go back to our discussion board, we said that in that case, if the value of the limit is 0, that means the numerator is growing slower than the denominator. Okay? So, limit of 0 means numerator is growing slower than the denominator. Okay, and then switching that around for our answer, that's going to mean that 5 to the 2x is growing faster than e to the 2x. Okay? Since we're talking about the denominator versus the numerator, that's going to mean 5 to the 2x, which is the denominator, is growing faster than e to the 2x, which was our numerator. Okay, so our answer for that one is it's growing faster. Now I don't want to do all the types of problems on this discussion board. So we got through part D. I just wanted to do maybe one more. In particular, I wanted to do part G. I'll let you try to figure out the other ones in our discussion board. It's similar to these problems. I don't think we have the log base 8 of x, but most of the other ones are similar. So I do want to jump to part G and do an example of that, but I think you can handle part E and part F here. So let me jump to part G, because that's the last one with a new trick in it. So for part G, we want to do, we're comparing the limit. We're comparing the growth rate using an infinite limit, and we have our numerator is going to be e to the 2x, and then our denominator, I was just looking at it, I already forgot it. Our denominator is going to be e to the 2x over 4. Okay? Alright, so if you think about this, this is actually the easiest one on the whole homework if you can just realize what you can do here. So e to the 2x over e to the 2x, those cancel out. Okay, so we can just cross out the e to the 2x on the top and the e to the 2x on the bottom. Why are we allowed to do that? Well, e to the u can never equal 0. So we're not dividing by 0 here, so we're not breaking anything. So what we got here is we actually just have the limit as x goes to infinity of 1 over 1/4. So in the numerator we have 1, and in the denominator we have 1/4. But if you're dividing by a fraction, that's the same as multiplying by the reciprocal. So if we just flip over 1/4, that's going to be 4 over 1. So it's the limit as x goes to infinity of 4 over 1. But the limit, even an infinite limit of a constant, is just a constant. So this is actually just going to equal 4 over 1, which is 4. Okay, and this was the third case that we haven't seen yet. So looking back at the discussion board, in the first case we said if the limit is infinity, the numerator is growing faster than the denominator. And then if the limit is 0, that means the numerator is growing slower than the denominator. But then the third case, which is actually case 2, if you look at the cases that are written on the discussion board description, is if the value of the limit is a constant other than 0, that means the numerator is growing at the same rate as the denominator. Okay? So let me write that down for your notes. If the value of the limit is a constant other than 0, that means the numerator and the denominator are growing at the same rate. The numerator and the denominator are growing at the same rate. Okay, and you might be wondering, well, why does that mean they're growing at the same rate? Well, relatively speaking, you only care about what the functions are doing as you're approaching infinity. So if the value of the infinite limit of those ratios is equal to a constant, that means that they're only off by a constant, which means that they're both, as you approach infinity, they're both going to be approaching it at basically the same rate. I know it's a little strange because you might think, well, since you got 4, doesn't that mean that maybe the numerator is growing 4 times as fast as the denominator? And yes, on the short term it means that, but in the long term, the limit as x goes to infinity, if it's just a constant, that technically means that relatively speaking, they're growing at the same rate. I know it's a little bit strange. But just being off by a constant isn't going to ultimately affect the rate at which you're growing, which is really a derivative. Okay? Because the derivative of a constant is 0 anyway, so it's not going to make any difference with the growth rate. But that's a little bit hard to explain, but it's pretty easy to calculate. Okay, well, thanks for watching. Have fun with the other parts of the discussion board. I think you should be good for those, hopefully, with this video.